There we go. Hello, everyone, and welcome to Handmade Hero, the show where we code a complete game live on stream. We are back for an exciting Monday after last Friday when we implemented hardware display of our game. So now we're actually going through the GPU to display our game. Thought that was going to take longer than it did. It turned out to really not take very long at all, which means here we are on Monday, and I don't necessarily know what we should be doing. There's a number of different things we could do. Like I said, there's a number of things on our list that we want to do, and I'm not sure what the most logical one is. And so there's I guess what I would say is it feels to me like probably the best thing to do is, since we had some momentum on the GPU stuff and people don't seem to be minding too much that we're doing GPU stuff, I think maybe the most convenient thing for us to do would just be to actually look a little more seriously at the GPU stuff and maybe show how to make our renderer go through the GPU so that we can basically pick which one we want to do, whether we want our software rendering or whether we want our GPU rendering. Because really that is incredibly simple to do. There's really not very much work involved in it, especially because we don't really even have to take a step into shaders to do that. A little later on in our game, we probably will have to do that because as we decide to add a little more lighting and stuff, we'll probably want, or I shouldn't just say want, probably just really need, for the most part, shaders to do what it is that we're going to want to do. And so at some point we'll have to do that, but even with just what I've taught so far, you can pretty much port the entire game except for one thing. So there's really only one hard thing that stands in our way of making that work. And that thing is how to get the textures, like basically the bitmaps that we're using for the game, like, you know, our little sprites. It's how to get those down to the card in a efficient fashion. And so if you recall how our architecture works at the moment, we don't have to think about that, because what happens is that when we find that we need an image or predict that we're going to need an image on a frame that's coming up soon, excuse me, we really don't have to do anything other than get it off the drive and then put it in memory in a location where our renderer can get it. And that's a very straightforward operation because it's entirely on the CPU and there's no need to communicate with the graphics card about anything there. All we need to do is have a flag basically on our side that says this thing has finished loading, you can now draw with it, so that the renderer doesn't try to draw with it before it's actually finished loading. That's really all we had to do. Now, when we go to doing this on the GPU, all of the rendering stuff can pretty much stay exactly the same as it did. And the reason for that is because the amount of command throughput that we're going to have is just not that complicated. In a 2D game like this, even if we have thousands of sprites on the screen, that's just not a really high amount of traffic to send down to the graphics card. But for our texture data, there is a lot of data. We're a 1920 by 1080 game. We've got a lot of full screen layers in like our cutscene, for example. So even just for the intro sequence alone, there's a lot that we might have to manage there, and we don't want to have a stuttery frame rate while we're doing transfers of stuff like those plates. And so we need to insert an extra stage in our asset streaming to be able to stream textures to the graphics card in some kind of a reasonable way, and that is not always as easy as it should be. There's nothing inherently complicated about it, but unfortunately GPUs were not designed to do it originally. That, you know, textures were typically not streamed in real time. They were uploaded during like a loading screen. And so nowadays, when you're actually trying to stream, the APIs aren't really set up for it. So you have to kind of go through some extension mechanisms to really do it, and not all cards support it well. Some are very buggy with it. There's sort of this concept of fencing you have to use to sort of do stuff like know when something is finished uploading. There's just a lot of complexity there. So I think maybe, you know, just what I'm leaning towards is maybe what we do is we port everything over and we just let our frame rate be very stuttery at the moment. When something needs to be downloaded to the card, we just do it and we accept the fact that it's stuttery, right? Maybe we do that. And then what we can do is look at that as a separate issue and choose to address it at whatever time it is that we feel is necessary. We would have to address it eventually. We can't really leave it that way. It'll have to get fixed at some point. But that's probably the way to keep things easy enough to understand at first without having to force people into too much of a GPU understanding right off the bat, because the rest of the stuff is relatively simple. So I think maybe that's what I'll start doing today, and that way we can sort of get that working, and then we can kind of get all that going. Maybe that's what we'll do this week, and then we'll sort of end with having the ability to switch between the two renderers, and then we can turn on VSync, which is one of the reasons I wanted to be able to go these paths. And we'd also then have a path that we would know would always be fast enough to run at 60 frames a second, 1920 by 1080, so we can also test with the GPU so it doesn't force our hand at forcing us to optimize our software rasterizer if that's not what we want to do in the short term, right? Which, let's be honest, I was never expecting the software renderer to run 1920 by 1080 by 60 frames a second. It was totally crazy that it ended up actually doing that. And so, you know, I don't necessarily want to sort of insert into the stream this constant need for us to go back and optimize that when that's really was never supposed to be a thing. It was mostly educational. The reason we were doing it just happened to be really fast. So anyway, let's go ahead and take a look at that. Now, today's day 238, so you're going to want to, if you're following along at home, if you pre-order the game on handmadehero.org, you're going to want to start with day 237's source code. That's what I'm starting with today. And just to sort of refresh your memory about where we left off, here is me running the game. And you can kind of see that this is exactly what we would have expected it to look like. Only now it's running through a graphics card instead of running through you know, a software renderer. And you can kind of see that everything still works the same way that it did. Now, if I remember correctly, I think there was a bug in my float conversion, because I feel like if we let this guy run, didn't we get to a point where there was a bug in the radix sort or something? And I'm guessing it probably wasn't actually in the radix sort. It's probably in my float to int conversion code. But I just feel like at some point here, maybe when it gets to the next scene, we had an assertion that the sort order wasn't correct. That's just my recollection, and I don't actually know if that's true. But I felt like that was true. Maybe not. Well, I don't know. Maybe we have to get to a further out scene. I'm not sure. I just felt like that was true. Is that not true? Well, I mean, I'm sure it'll crop up again if I'm not mistaken. Next time we kind of leave it running. So I guess I don't have to worry about that for now, because you know, next time we sort of preview our cutscene, it should happen if it's going to happen. So I don't know what's going on there. Oh, that's interesting. So in this sort, we have two things at the same Z level, and you can see that Santa Claus has moved behind the background, which is not good, right? So now that we're sorting in Z, we kind of have to deal with that. Although we could also have a way for cutscenes and stuff like that to turn off the Z sorting entirely if we wanted to, since we don't actually want Z sorting for this. But it's worth noting. So it looks kind of like maybe I'm wrong about that. I don't know. I thought there was a bug, but maybe there wasn't. We'll see if it crops up again, and we'll take a look at it if it does. Okay, so here we go. Let's go ahead and talk about what we're going to do here. So right now you can kind of see what happens where we have our rendering. We have a very sort of properly, in my opinion, walled off renderer, in the sense that we don't really count on very much about the renderer in the external code. So really all that happens is we call, like, you know, tiled render group to output and stuff like that. That's really all that happens. So we push a bunch of stuff on that are, like, you know, instructions to the renderer to do something specific, and then we call, like, this tiled render group to output, and then we call end render, and that's really all there is to it, right? So it's not super hands-on, and that's somewhat intentional, Because the idea here is that I've kind of known all along that the renderer is something that may want to be swapped out. For example, in the exact case that we're talking about here, where we have a software one and then we also want to have a hardware one, right? And even if you didn't want to have software and hardware, you might, for example, have two different hardware ones. For example, people ask about Vulkan or Direct3D and that sort of stuff. Well, if someone was going to port the renderer to one of those other APIs, you may be on a driver that doesn't support, say, Vulkan yet. And so if you have a Vulkan path, you may still need to have an OpenGL like fallback path, right? Or similarly, if you have like a DirectX 12 path, you may need a fallback path for machines that don't have DirectX 12, right? Maybe you're running on Windows 7, which doesn't run DirectX 12. So it's just kind of one of those things that if you're a professional game programmer, you have probably gotten into the habit, just by nothing other than experience, of keeping the renderer sort of separated out even before you get to the point where you really need to. Now, is it essential to do that ahead of time? No. It's always fine to sort of like, again, use a more compression-oriented approach and like start separating it out at the time that you need to. But because that's just something that I, am just well aware of, I just tend to write renderers from the start at this point to be fairly modular in that sense. So it's already set up to be pretty reasonable as something that can be swapped out, but it's not quite there yet, right? We haven't done the work of really truly separating it out. And so what I'd like to do now is start to extract it out in its entirety, so that we really can choose which, how we want to actually render things, whether we want them to be hardware or software based. And so there's a couple different ways we can do this, and it depends on how much code we actually want to share. Now you can kind of look at our render group in here, and this is all the code for the software renderer, right? But if you actually take a look at where the work actually gets done, we do our sort entries, for example, and then we go into sort of this do-tiled render work thing. And the do-tiled render work, I always fail at searching for that because it's wrapped in, the Emacs can't find it because it's wrapped in this platform work queue callback thing. But really, this thing right here, render group to output, this is where all of the time is spent, right? It's all of the time is spent going through these things and calling one of these rendering functions. And specifically for our purposes, obviously we optimize the expensive one. So draw rectangle quickly is really the one that we're spending most of our time in. Almost everything goes through that path, okay? And what you'll notice about this is really all of the stuff that actually determines what the game looks like on screen goes through this function. So if we want to render to a piece of hardware, instead of rendering to, instead of rendering through our software renderer, really all we have to do is produce a new version of this function that instead of dispatching to our software renderer, dispatches to, say, OpenGL. So I'm just going to literally start by doing exactly that thing. So I'm going to go ahead here and, we're going to open up Win32 Handmade, and I'm going to make a new file that's like Handmade OpenGL render group. And really what this is, and you know what, honestly, I don't even know if that name needs to be that long. I'm just going to call it Handmade OpenGL. And we're just going to start with that and say that we'll just put whatever OpenGL stuff is in there, okay? And so here is our render group to output call, okay? And I'm just going to literally translate this into something that, I think will work with OpenGL. And so what we can see here is that this entry coordinate system thing, that was always a test thing. We don't really need that at the moment at all, right? That's not doing anything. And so I can literally just leave that case and not do anything with it, okay? We've got this guy here, which is how we draw most of our sprites. We've got clear, and we've got rectangle. So far, that's all we actually have to deal with in our render. It's really, it's very, very straightforward, right? It's very simple. And so if we take a look at what happens now, does this sort entries thing ever even get called? It doesn't, does it? So it's really just so sorted. Oh, well, it kind of gets used right here, I guess. So anyway, if we take a look at what actually happens in this routine, it's not really particularly difficult to imagine replacing this very small number of operations that we have to do with their equivalents in OpenGL. Now, clear, right, we've already seen how that works. So there really wouldn't be anything magic for us to do about clear. We could literally just come in here and do exactly what this says. We have a color value here, right? And we know the target width and height. So really, everything that we might want to do here is really straightforward for us. I'm going to go ahead and pull this out here temporarily just for another reason that we'll talk about in a second. But so if I wanted to clear, we just need to know what the color is, and then we do the color buffer bit clear. That's really it. And of course, the color, if we go look at what the color actually is, inside handmade render group.h, we've got that clear entry. Where is that guy? It's just a v4. So, you know, literally we can just pass this thing down exactly as it is, and we really shouldn't have to do anything else. Okay? So passing that down and clearing, that would be a complete implementation of the clear command. That's it. So that's nice. And now, we're just left with two ways to fill a rectangle. One way to fill a rectangle, we have to actually do it with a solid color, and the other way we have to do it with an image, right? So the image one's going to be the hard one for the reason that I was talking about before. It's because we really don't have any notion at the moment of how we're going to background load those things, so that's going to be an issue. But we'll cross that bridge when we come to it. For now, what we'll do is let's just say that we draw both of these basically the same way. So we're going to draw them both as solid colored rectangles. We'll just do that for now, and then we'll kind of go from there. All right, so if we start by doing that, let's see. If you take a look at what happens here, this is our rectangle. Our rectangle goes from here to here, and it's in this color. So if that's what we're trying to do, if this is essentially our min p, you know what I'm saying? And this is our max p in terms of where they are on the screen. And here's our color that we're going to do for our rectangle. If that's what we're looking at, then again, we already pretty much learned exactly how to do this. In fact, we really learned already how to do all of these things, right? You can kind of see how I was doing these here with this GL begin triangles thing. We already sort of have exactly the code that we're doing for this, so we could do that exact same code with really no effort, right? We could just go ahead and say, all right, go ahead and draw some triangles here. And instead of like negative p, p, that sort of thing, instead of drawing it that way, let's just use our min p x, right? And our min p y, that sort of thing. And then this would be our max p x. This would be our min p y. I mean, essentially, I'm just doing negative p with min p is all I'm doing, and p with max p, right? That's all we're talking about, and that's it. Now, there is actually even a, I don't know that we actually want to do this, but we can, you can even, if you want to, when you're passing a vector, there's a fv style call, like where you pass a vector, where you actually just pass a pointer to the floats. I'm not going to do that because we mix and match a fair bit here, so I'm not going to bother doing that. But I just wanted to kind of point it out that it's there. You can actually pass vectors to OpenGL that way, just as arrays of floats. So we have our min p, we have a max p min p, right? A 1 0. We have max max, min min, max max, and min max. That looks right to me. So that would draw our triangle. Now we do have one problem that you'll notice here that we'd have to solve fairly soon, which is that this brings up the coordinate problem again, which is that remember we talked about the unit cube. All of these coordinates are in the unit cube, and we don't have yet a projection matrix that will actually give us something that would correctly map us into the unit cube for these coordinates that we're passing, which are actually screen space coordinates that we've already transformed. So that's a problem. But other than that, this would do exactly what we would want it to do, right? And so in both cases, for rectangles, we could do exactly this. In fact, we could really do the same exact thing. We could just have a function up here, which is like rectangle vertices or something like this. Or I guess I should say just rectangle, OpenGL rectangle, I don't know, something like this. And we could just have this be something that you pass these to, and then we can just use it, right? So we can say, okay, there's a min p, there's a max p, there's a color, oops, and that's it, right? And so that's pretty straightforward. The color value, we would probably just do like so, because the entire thing typically has a color value and it's not interpolated. So that's roughly what that would look like. And off we would go. So there's our OpenGL rectangle. Now there's a number of reasons why we probably won't end up doing it exactly this way. And the reason for that is because this is just a lot of function calls and stuff. And when we get up to higher numbers of primitives, we're going to want to do these in a more efficient way. And in fact, OpenGL has more efficient ways of doing it that we'll look at a little bit later. And basically what they involve is packing all of these things into one buffer. So we just write out a big buffer, and then we just say, hey, OpenGL, take this whole buffer as if it's a bunch of vertices and draw it that way, right? So, you know, don't be deceived. Although this looks like just a lot of business happening here, and it's like, wow, that's a lot of function calls going on for every rectangle or whatever. Yes, that's true, but really we'll be able to flatten that down into just one function call sort of as we, after we get everything working and want to start just concentrating on cleaning up the usage a little bit more. So don't let that bother you too much. It's really not an issue, but it's usually best to kind of leave it this way when you're first learning because you can see exactly what's going on, and it's a lot easier. You don't have to worry about what is OpenGL, how is OpenGL parsing your buffer, and did you pass it the right sort of way to decode it and all that stuff. So there's a lot of business that comes in with the parsing. That's why you may want to not, you know, just not quite do that at first. That's why I'm not showing that as the first thing we do. So we can do this in both cases here. We have the entry color. I can now convert this to basically doing the same thing that it was doing before, but calling our OpenGL version of the function. So there we go. There's the OpenGL rectangle for that. In this case, we have essentially the same thing, but we've got to do a little bit differently. So here's our entry P. I believe our entry P, it's like these two vectors are what stretch to the other side. So in this case, we probably want to actually compute that max P. And I guess in this case, maybe we do actually both of these. So we've got our min P is going to be the entry P, and our max P is going to be, you know, sort of the thing stretched, or sorry, displaced by these to get to the other corner, right? So there's our min P. And then entry color is still the same. So really, if you take a look at what this turns out to be here, I guess I also don't know why do we pass null pixels to meters to that function? Does anyone know? What is that used for? Absolutely nothing. All right. I think that was only for when we had lighting, and I guess we still pass it for some reason that's not immediately clear, but it looks like that can just completely go away. Right. So there's, I mean, at the risk of sort of being overly dismissive of how hard it is to get a software, to get a hardware renderer working, hey, since there's just a ton of hardware there to do everything for you, really, honestly, this is basically what what it looks like. And so we really just have to do a few simple things. To start with, we would have to obviously set up the viewport to be based on whatever the output thing was here, like so. But really, that's about it. There's not really a whole lot more to it. So we have to do that to get ourselves set up correctly for drawing. But other than that, it's really not that complicated. So let's talk a little bit about the things that we're not doing yet. So we're not doing the texturing, so we need to do this part right here. So that part's not done. Our rectangles are basically done. It's just our texturing isn't done. So we need to figure out a way to do the texturing part of it. So that's one thing. But the other thing that we need to do is, like I said, we need to now establish a screen space, because what we did before, again, was just actually give it coordinates that were the unit cube. And that doesn't really help us when we actually have to start drawing individual rectangles at different places on the screen. So what we want to do now is we want to be able to set up our matrices so that our projection matrix, when OpenGL actually uses the projection matrix, that projection matrix actually maps our coordinates into the unit cube for us from our screen space. Okay, that's what we would like. That's what we would like to have happen. Okay, so how do we do that? Well, if you've been paying attention to our maths, and you know maths, the plural, of course, coming from the Britain, then you should actually kind of already have an idea of how we would do this. This is not really a mystery, and it's not particularly complicated. Sometimes it can take a little while to get right because, hey, there's enough sort of fuzzy things around that could be possible, but in general, pretty basic. Here is how this works, right? As I told you before, in OpenGL, what happens is we have a point in clip space, and that gets computed from the points that we pass in, right? So our actual P gets passed in, and it's multiplied by M projection, a projection matrix, and an M model view, right? And like I was saying before, although we haven't really covered this much in Handmade Hero, these are actually multiplied together. So for all intents and purposes, it's just one matrix. It's just like what we do know. There's really just one M. And since we have set our model view matrix to the identity matrix, which means it doesn't do anything, essentially our entire OpenGL fixed function pipeline operation at this point looks like this. Okay? This is all we're doing. So we're literally just doing a P prime equals MP, the most basic vector transform you could possibly do. We're multiplying a 4. This is a 4 element, right? This is a 4 by 4, and producing another 4. And remember, the reason it's 4 is because it's X, Y, Z, W. It's got that synthetic coordinate. Now, in our case, we don't use Z, right? We're not actually using Z because we've handled that. So this is Z is always 0, right? For all intents and purposes, we don't care what it is. And since we're transferring points, W is always 1. So really, we're just talking about X, Y, 0, 1 is the vector we're always transforming. And M is this matrix that we can set up to be whatever we want. So we know that we're trying to produce a P prime here that has the structure that looks like this. We want Z to stay 0, or really, honestly, we don't care. It doesn't matter what Z is at all to us, to be honest. So we don't really care what Z actually is, beyond just respecting what OpenGL needs it to be. And trying to think of how to say this. Essentially, there's a step that we have not talked about that occurs after you do your transform, and that is if you are trying to do the perspective stuff that we covered a while back. What happens is whenever you transform, you end up with something in the W coordinate, and OpenGL will divide the vector by whatever that value is. So if the W coordinate is like 3 or something, it will divide this out to produce a 1. So it will divide everything by 3. The reason it does that is that's the hacked way, and hacked may be a strong term. There's a little bit of mathematical rigor to it. But the reason for that is, if you remember how we did our divide by Z thing to sort of get the perspective so that things shrink as they get further from the camera, that's how they work that in there. Because remember, a matrix transform is always linear. And dividing by Z is totally not linear, right? Just to be completely clear, even if I was just to talk about the single variable Z, that's Z to the first power. That's linear, right? And we're talking about something that is now doing Z to some kind of an inverse power, right? It would be z to the -1 power, right? It'd be 1 over z, which is in no way to the power of 1. So basically, the way that they hack that into the pipeline to make it sort of still feel like it's all matrixy is it's specified that after you do this matrix transformation, you divide by the w coordinate to quote unquote renormalize, right? Or rehomogenize those coordinates where w is always going to be equal to 1. I don't really know what to say about it. It's not. We could kind of go into that in a little more detail, but I'd rather just kind of leave that be for now, because it's more of a topic for when you're starting to think about how to do 3D transforms with these, and we just don't have that in Handmade Hero. We've already talked about how to handle perspective with Z, and so really it's just kind of a topic that's super not relevant here. So point being, we're going to leave that bottom part. We're just not really going to think about that much. We're just going to assume that we come out with a 0 and 1 here, and we're going to make that be true. So it's really just the x and the y that we care about, right? And this part that has to be in clip space, like I said, clip space is this sort of synthetic coordinate system where -1 is over here. This is -1, -1. This is 1, 1, right? I probably shouldn't have bothered drawing that there. And so it's sort of this dimension 2 cube, right? It's sort of radius 1 in all directions, you might say. And what we need to do is we need to map the entire visible screen into this space, which means that in order to do the coordinate system we want, where our coordinates are currently like 0 to width of the screen or something like that, that's what we have. We need to essentially divide and displace our values so that 0 ends up being mapped to -1 and width ends up being mapped to 1, right? That's what we actually need to have happen here. And I agree it's kind of stupid that we have to do that, because OpenGL is then just going to turn right back around and remap -1 and 1 to 0 to width. So we're literally doing this for no other reason than to shoehorn it into the GPU's concept of what the graphics pipeline is supposed to look like. Oh well, life is hard. But a small price to pay to access all the power on the GPU, so, who cares? So anyway, so that's what we actually have to do, and so that's what we have to set up our matrix to do. So what we're essentially doing here is we're saying, okay, we need to set up a matrix, and we can really think of these matrices in a more simplified fashion when we don't care what those bottom values, we don't have to do anything to the bottom values. If we know that we're inputting something that looks like this, and we know that we're outputting something that looks like this, right? Then it tells us some things about this matrix that allow us to sort of, by default, fill in some values, so we don't have to think too hard about a bunch of the different values. For example, if this has to be equal to 1, well, the x and the y value that's coming in here obviously can't be multiplied by anything, because if they were, we might end up with a non-1 value here. So essentially, all we want at the bottom is just something that reproduces the 1. So we want to knock out all of these terms and just be left with the 1. Technically, we could put anything we wanted here because this is always 0, but it seems like better to leave it 0 so that we know even if we pass the z coordinate, we'd still get a 1. Okay? So we know that. We want this to come through as 0. We don't want anything in there at the moment. Not that it really matters. So since this is a 0 and this is a 0, I feel like maybe we just treat that as a pass-through. So that, again, would be almost exactly the same. It's just the identity matrix kind of portions here. So that way we just take whatever's in here and we pass it through here, right? And that seems fine. And then furthermore, this value, we never want to affect these values. So we're essentially saying that when whatever it gets multiplied by in these, remember, because it's going to be x times this location, y times this location, plus, this times this location plus this times this location, you can kind of see that we already know that we don't want our z value ever to affect anything. So even if it wasn't 0, we want to make sure that it doesn't actually affect our x and y for the time being, because that's not something we actually wanted to have happen. So really what that means is we're left with just some very specific places here. We're left with essentially something that looks like this, right? Something sort of like this. And what we can sort of see about the equation as this comes out, I don't know, can I erase? There we go. What we can see about what happens to this equation, if we assume a priori that this is what it's going to look like, is that we'd have ax plus by plus e, right? If I'm just doing the multiplication here, right? Ax, by, e. And then I was going to just do the exact same thing here. Cx plus dy plus f. Right, there we go. So if you take a look at what happens there, these are our equations that we know we're going to have as a result. And so we can, using these equations, sort of figure out what our what values we want to put in for these coefficients in our matrix to give us the transform that we want. So what we know now is we want, right, ax plus by plus e, right? That's our x coordinate. We want that equation to essentially be something that takes in, right? We're trying to produce a function that takes in an x value and outputs a new x value, such that this was in the range from 0 to width, and this is in the range of -1 to 1. Okay? So what we know is that, for example, since we're not rotating things, we can pretty much say one additional thing. Since the y value doesn't have any participation here, like it doesn't matter what the y value is for our computation of the x, we can also say that like these terms, similarly the x doesn't have any computation, we could say that these terms also are irrelevant, right? Because we're not rotating anything. So we don't ever need the y component to move into the x space or vice versa. So we can also kind of get rid of these, all right? So we're down to a really, really simple equation. We're basically saying f of x, equals ax plus e here in this case. And we're saying f of y equals dy plus f. In this case, we've got a little bit of too many f's here, but oh well, life goes on. In fact, this is probably a g. It's a separate function, right? So we've got these two functions, and we just want something that does this mapping. And it's pretty easy for us to figure out what that would be, right? Because this mapping defines exactly what we want. We know that for x, for example, our f of 0, we want to be equal to -1. And we know that our f of width, we want to be equal to 1. And that's two sort of equations we have, right? And we only have two unknowns, a and e. So if you write this out, right? If you write this out, just substituting, if x is 0, then we would have a times 0 plus e equals -1. And that immediately just tells us that e equals -1, right? Because that term goes away. So there, we're done. We solved one term, right? And f of width equals 1. Well, then we know, again, multiplying this, or rather expanding this out, we would just have a times width plus e equals 1. We know that e is -1, right? Yeah, I'm sorry. It's right up above there. Not sure why I'm forgetting. So we have a width -1 equals 1, or a width equals 2, right? And hey, guess what? You divide this out, and you get width, or sorry, a equals 2 over width. Right? So that lets us know exactly what our function for f is in this case, and it allows us to fill in our matrix exactly what we wanted. Our e in this case is a -1. Our a in this case is a 2 over width. And you can kind of see why that is, right? It's because we're trying to expand it to a thing that's 2 units wide, right? Remember, our unit cube is 2 units wide. We're trying to expand this thing as 2 units wide. We're trying to get rid of the fact that it goes from 0 to width. We want it to be 0 to 1 so we can map it as a unit interval, right? So we're dividing by width to normalize this to 0 to 1, right? We're multiplying by 2 to blow it out to a 2 wide thing. And then we're offsetting it by that 1 to make sure that we shift it back over so that it starts at -1 instead of 0. So you can see that we solved the math purely algebraically, but it makes concrete sense when we look at it over here. And hey, big surprise, these equations are exactly the same, so we don't even have to solve the other one. We know it's just going to be 2 over height and -1, right? So that tells us exactly what our matrix looks like now. Our matrix is just this matrix, right? It's the 2 over width. Wow, that's really bad handwriting. 2 over width, 0, 0, 0, oh, sorry, -1. 0, 2 over height, 0, -1, 0, 0, 1, 0, and 0, 0, 0, 1. Okay? And that's the thing that will compress us down into that unit cube. So, we probably don't want to jump right into trying that right away because, hey, we've got all this other work over here to we don't even know how we're going to call this function, this Handmade OpenGL function. So what we can do instead is we can jump over to the stuff that we already have working, right? Because, we've got this thing over here where we've got this code working where we're drawing stuff. We should be able to test it over here because, we only got like 15 minutes left. We probably don't have time to get all the rest of the stuff working over there today, right? Let's test just that one piece over here and get that working in something that we know works. So let's shift this. Remember, we fixed this by just directly passing the coordinates to the unit cube. Let's go back to doing it the way we were doing it before. Let's go back to doing it with... in fact, what we could do? We could just use the min-p, max-p thing we were doing over here, right? We could just take this OpenGL rectangle thing, exactly how it is. Here's that, like so. Let's get rid of that. So there's our OpenGL rectangle function. And I guess we, at the moment, we could still leave the color thing in here, I suppose. We could just say that the color is... all ones, just white. So we can still do exactly this thing, and now we can specify our min-p and our max-p, like so. So we know our min-p is just going to be 0, 0, and we know our max-p is going to be buffer width, buffer height, I believe. Or sorry, window width, window height. Is that correct? No, that's not correct. That's not correct at all. We actually want it. It's in terms of the buffer, I believe, right? At the moment, there's some aspect ratio stuff we would want to do here. In fact, I'll mention that to decide how we want to handle aspect ratio, black bars or crop. So yeah, it's not really that. It's actually the buffer width and the buffer height, right? Because that's the actual size that we're trying to fit into the display. So I believe that would be a more correct way of looking at it, probably. But you could, it's 6 to 1/2 dozen the other. It depends on exactly what you're trying to do. So you could pass either there, and it would just have different behavior when the window isn't the same size as the back buffer. If they're the same size, it won't matter. So anyway, that's an example of that. And now if we run it, we'll go back to the old bug we have. Right, where we've kind of got this thing where we're drawing in the wrong place, and we're drawing I know you can't probably tell exactly what's going on there, but we're basically drawing 1 pixel of our bitmap, right? It's totally wrong because it's huge. Remember, the whole thing is specified from -1 to 1, and we're passing 19, 20, we're passing something that's 1,000 times the screen size as the coordinate, over in the corner. Not what we would want, right? So let's go ahead and try to fix that with our projection matrix. So we have load identity here. What we're going to want to do now is learn one new OpenGL call, which is a way to load something other than the identity. So what we want to do is do load matrix call. And there's a couple of different ones of these, which I'll kind of show you now. They basically are the same as sort of the other ones where you say, what kind of matrix are you passing? Let me find something here that's a documentation for it. The service is unavailable. Okay. I don't know what that means. I don't want Stack Overflow. I want like a spec page, please. How about this? Is this, that doesn't seem to be loading. Here we go. All right. So here you can see GL load matrix D and GL load matrix F, the two flavors of this. And again, like I said, it's kind of almost like a Hungarian notation sort of a thing. It's not really as bad as Hungarian notation. It's actually kind of good because in this case, unlike Hungarian notation, which is completely useless, this actually differentiates these two functions for a calling program like if it was in C, where you can't overload functions. That's kind of there to prevent that, right? So it's not bad like Hungarian notation. It's not superfluous like Hungarian notation is. We're not passing doubles. That's what the D stands for. We're passing floats, so we're going to be calling load matrix F, right? And as you can see, we're expected to pass a GL float here. So what we need is we need an array of floats that comprises the matrix. So we need our projection matrix here, and we need to specify, you know, the actual matrix that we just talked about. Now here is, the identity matrix. So if we wanted to, you could sort of imagine this being the identity matrix, like so. That would be what that would look like, and I guess I should probably do it like this, because we wouldn't be able to use those initializers there. So there's the matrix, and when we do GL load matrix F, we can basically just pass it a pointer to any array of 16 floats, and it will just load that in place of the current projection matrix. It will replace it, which is what we want. But as soon as we start to do anything more complicated with this matrix, we run into a particular problem. Now, what we can do right off the bat is we can put in our terms here, like I said, where we had kind of our 2 over width, right, and our 2 over height, that. And I don't know if we have our math support in here. I don't remember if we do or not, but we probably want to use a safe ratio 1 here, just because, remember, there's nothing that says that our buffer width might not be 0 in some weird kind of unusual case. So, you know, we might want to go ahead and take a little bit of a precaution there to make sure that we don't divide by 0 in that case and just go nuts, go haywire. So those will be fine no matter what we do, but we then need to put in our -1s here. And there's a problem with this that we'll talk about in a second. That's why I can't just literally think of it like that necessarily. Okay, so we don't have math in here. Can we just get math in here? Is there any reason we can't just include the math library? Square root is not found. Where is square root normally found? Dare I ask? Intrinsics? Looks like intrinsics. And so, you know, like if, assuming we did all our math right and assuming everything else is fine, you know, we would expect this to just work with the projection matrix as so, but of course it doesn't. Although that looks broken for other reasons, so don't take that with a slight grain of salt. But point being, this is wrong already, even before that. At least if I remember correctly. And the reason for that is because of an encoding issue. And let me explain to you what that encoding issue is. When I draw this, you notice I'm just drawing out a matrix the way that you would see it in a math book. And that's totally fine. We all understand what this is. And I kind of showed you something that tells you how this matrix works, because I showed you matrix multiplication. I said, oh, we kind of go like this and we go like that. We take the x, multiply the x, the y by the y positions, you know, z by z, w by w, and we go like this. What that means is you now know the structure of this matrix and what its values mean by looking at it, because we've defined the operations on it and it's all clear what's going on. Okay? So there's no ambiguity when I show you this. And furthermore, there's no ambiguity in math, because math writes things such that column vectors multiply this way. If you wanted to multiply the other way, you could write a row vector, right? I could write, you know, sort of a vector that looked like this. And then, if I was doing multiplication that way, you would see a different type of equation emerge, right? it would be x times the x position here, the y times the y position here, the z times the z position here, and it would go by columns, the multiplication, right? The matrices columns would get multiplied in here, not the rows, right? And that's a pretty important distinction to understand. Now, in math, you have both of those things. In math, it's just matrix multiplication is defined anytime you have two matrices, because a vector is just a small matrix, right? A vector is just a matrix that only has a 1 for one of its dimensions. But math is defined just fine as long as the number of columns of the input matches the number of rows, of the left-hand side, matches the number of rows on the right-hand side, right? That's all it cares about. It doesn't care about anything else. As long as that was true, which it is in both cases, right? We're fine. And it'll just generate a different size thing as the result if you add more, right? If I added more in here, we would just generate a bigger result. But the math is still defined. Now, it breaks down if I don't do that. If I tried to do it where I was just doing two elements here, it would break down because you'd multiply this by this, this by this, and you get to here and you'd be like, I don't know what to do. The math is not defined anymore. What does it multiply? There's nothing to multiply it by, right? Similarly, I couldn't get rid of these two, same reason. I also couldn't get rid of these because then these would have nothing to multiply by, right? But as long as it's defined, as long as the number of rows in the left side and the number of columns on the right agree, we're fine. So the math just works and the math is clear and we all know what's going on there. But once that math has to happen inside a computer, we have a problem. Okay? These are just arrays. They're just memory locations. They're just a series of floating point values that come one after the other. There is no rigid rule inside the computer about which way you were specifying your matrix. For example, when I say you want to multiply a matrix times a vector, well, OpenGL or anybody else doesn't know whether that means, right, that I've got this happening, right, and my matrix is defined that way, or whether I've got this happening and my matrix is defined this way, right? And you might ask, well, what's the difference? The difference is where these values would appear, right? And furthermore, we don't know how it chooses to store the things in this matrix, whether it's going to store them like, say, this way. So this is the first value, this is the fourth value, then we go to this one's the fifth value, and so on. Or whether it chooses to store them this way. So there's all this ambiguity in here, and you have to make sure that you get it right. Okay? And so the way that it looks if we write it out in C to match the math, if I remember correctly, is not the way that OpenGL's fixed function pipeline happens to work. OpenGL's fixed function pipeline, I believe, goes down, considers multiplication by columns. So it's as if the vectors were silently row vectors, actually. And so it goes like safe ratio 0, 0, -1. The -1 would actually happen over here. Right? Now I'm going to go ahead and verify that because, like I said, it's been a long time since I've used the fixed function pipeline. And so, you know, I might very well be misremembering that fact. But I believe that you need to put those in there. Now I'm going to take a little shortcut here, or rather just a little, I'm going to condense this just a little more cleanly, just so you can read the matrix a little bit better. Okay? So now you can kind of see it a little more clearly. But I believe that's the way it has to go. Now I'm going to hope that this documentation has it. But let's take a look here. And yeah, you can actually see just right from this definition. So here they've written it out in math form for us, and take a look at the indices, right? It goes straight down the column. There's the 0, the 1, the 2, the 3, right? Which is exactly not how C would interpret it, right? So they are assuming that the things go in columns, which means it has to look like this. So this is really the more correct projection matrix for what we're doing, right? And so now as we get, well, okay, so there we go. So I guess there were no other problems. We got exactly what we expected. And I just wasn't sure I thought there might have been one other problem in there. But anyway, now we've got something which actually takes screen coordinates in and produces what we would have expected. So now we're basically out of time, but we've done what we wanted to do here. And so I think we're in perfect position for tomorrow to basically have our render reported over. Because if you look at what has to happen, again, very, very straightforward. Really all we need to do is just go ahead and set up this same thing. So we're talking about literally calling this exact same stuff, essentially as the preamble to what's going on here. This would literally just be like the output target window width, output target window height. And then we'd load it in. We'd literally do exactly the same stuff, and then we would be done. And so we're not that far from actually having a fully implemented hardware renderer just at a very basic level. Really all we're going to have to deal with is just doing a little bit of the integration to make sure we can call this function from the right place and that swap buffers will happen properly and that sort of stuff, and then deal with that texture bit. But that's really it. So hopefully you guys understood that. I know there's a little bit of matrix stuff in there, and maybe you guys aren't as comfortable with matrices. We did kind of cover them, but maybe we need to cover them again. If that's so, let me know. But for now, let's go ahead and go to the Q&A so I can answer any questions that you guys might have about that. Let me see if I can kind of get here. I don't know if we're actually... I think we're working. Are we working? Sometimes the computer decides to stop paying attention to the chat. I need to get this machine using the automated Q colon thing. It's not using it. I'm still got to read the chat manually on this machine, which is kind of annoying, but... all right. Insobot was pretty great there, by the way. Boorox998. What keyboard layout do you use? Oh, just normal, the normal standard US keyboard layout. Huber Caleb, will Handmade OpenGL be included in the platform layer or game layer? It will actually be in the game layer, and the reason for that, although it's sort of technically a third tier in between the two, but it doesn't go in the platform specific layer because it can be shared between multiple implementations of OpenGL. So you don't want it welded. The reason you don't weld it into the Win32 layer is because then you have to rewrite it all again for Mac, even though it's 99% the same. So typically you end up having the Handmade OpenGL thing as a separate platform clean. You don't want to use any platform stuff in there, and that way you can reuse it. And so you wiggle swap buffers, that will still live out in the platform layer, but all the generic OpenGL will live in a file that can be reused in multiple platforms. I see no other cues. Elvin jumped in a bit late. So are we using the fixed function OpenGL API right now, or will we write our own matrix struct at some point? I'm not sure that's an or question. I think the answer to both of those is yes. Right now we're using the fixed function API. When we switch to using shaders, I don't know that we'll have our own matrix struct, but we would obviously be passing the shader will do the transform at that point. So technically it's our matrix at that point, and we can use it in whichever order we want. But that's kind of a separate thing that's neither here nor there. Oz method, wrist braces recommended for programmers in general or just something you've had issues with? I'm not really qualified to ask. I'm not really a physical therapist. I think it probably depends on the person. Cuber Caleb, if you include Handmade OpenGL in the game layer, won't that force you to include Windows.h and all the OpenGL headers in the game layer? So no, to be clear, remember, everything gets built sort of together, right? So it doesn't really matter for our purposes what is in what layer, because everything gets built as one giant file. So the important part really has nothing to do with whether or not you put it before or after the Windows.h, right? Because you can easily just put it after Windows.h. That's where it comes, right? That's pretty trivial. The important part that I want to sort of hammer home is you just don't want to use any non-OpenGL calls in this file. Because if you use Windows-specific calls, like let's say we put wiggle swap buffers in here, then all of a sudden the Mac port can't use this file, even though otherwise it would have been able to. And so the idea is you want to keep your OpenGL file, even though it is platform-specific in the sense that it's calling the OS, you actually don't want to make it be platform-specific because you want to be able to reuse it in all of the different platforms. So basically what will happen is like the Win32 platform file will pound include the handmade OpenGL.cpp file, and so will the Apple one, right? That's how you do that. Grizzly Ninja, was push buffer rendering primarily in the software renderer because the real hardware renderer works that way due to GPUs? No, it's in the software renderer because of sorting. Remember, we never would have been able to implement our sorting if we hadn't have gone with the push buffer style. And so really in a 2D game where you know you're going to want to sort for transparency reasons to get better compositing and stuff, and potentially for performance as well, you got to do deferred. You got to wait. You got to just buffer and then render later, because otherwise you can't sort, and you need to sort, right? Pix1234, will the game be given away to dev viewers for free? No. It is pre-orderable, in fact, on handmadehero.org. It's right there. Off topic, have you worked with, talked to, or met Andre Lamothe before? No on all 3 counts. I, in fact, have not even ever read something by Andre Lamothe. So I literally have no contact with Andre Lamothe in any way other than that I know he wrote some books. That is really all I could say about what I know about Andre Lamothe. Lost TGM, I feel uncomfortable with floating points representing pixels. Have you ever had problems with OpenGL and floating point values, like passing them to shaders or texture coordinates? So I'm not sure exactly what you're saying, but I'm gonna take a guess maybe at what you're saying, and you can correct me if I'm wrong. But are you basically saying that you're uncomfortable with knowing what will happen when you pass a floating point value in terms of where it lands on the pixels themselves? Is that what you mean, or do you mean something else? If that's what you mean, that is not only would I say that that's very normal, I would actually say that probably the vast majority of programmers have no idea what happens when they pass floating point coordinates to OpenGL. And a lot of times they get it wrong. And I think honestly the fault of that is mostly with the OpenGL materials. Don't start with a really clear diagram of how texture coordinates and and pixels work together and how pixel coordinates work together, that stuff is all very rigorously defined, and at least nowadays, as far as I know, all graphics cards properly obey a rigorous specification for what exactly it means to specify a floating point value and have it mapped to pixels. But that wasn't always the case. So one thing we could do on Handmade here at some point, maybe I'll have to schedule something for this, is to actually talk about that. We don't really have a lot of occasion to need to know in our particular case, but that's not to say that it wouldn't be good to cover it, because it does happen, it does come up. Do you use any element buffer or VBO in your OpenGL? Wait, where did that go? Let's see. Do you use any element buffers or vertex buffers in your OpenGL? If no, why? The answer is that we will be using vertex buffers in the OpenGL code. And the reason for that is because the function call overhead of doing GL vertex calls is not really, we don't want it. There's no need for it. We're just, the way that our renderer is set up, it just needs to stream a large number of rectangles, essentially, out to the graphics card and say, I need you to draw all these rectangles with these textures. And so there's no real need for us to do that. Now, unfortunately for us, and we can try to take steps to avoid this, but I don't know to what degree we'll want to. But unfortunately for us, we do have a problem, which is that the majority of systems that we're probably going to run on, certainly at the low end, do not allow you to set textures out of a buffer. You can do that on, say, like NVIDIA hardware. You can do fully bindless graphics where you're literally just specifying like what texture you're drawing with on a per element basis. But you can't do that in the general case, at least not yet. And so we will have the problem of our vertex buffer scheme will not be particularly fast, or at least not as fast as we might like it to be, because we won't probably bother packing our textures into texture pages. Like, maybe we will, maybe we won't, but it depends. Like, we could have our asset packer do that potentially, but it's hard to say, right? There's a lot of downsides to doing it as well in terms of the streaming and all these other things. So it's unclear like what we want to do with that. But we will be doing vertex buffer objects just because there's no point in having the functional overhead for building the rectangle stuff. But it won't be really that much of a speed win because a lot of our time will be spent switching textures, I would suspect. That's my guess anyway. At the moment, we're not using them yet because I only just barely taught people how to do OpenGL at all. So before we switch to using those, we will have the pipeline working in fixed function with no buffer objects, and then we'll switch it over. But it's purely an optimization as well. There's no difference. Like, it doesn't do anything different. It's just an optimization to get rid of the function calls. Did you do your own GL ortho call when you set up the projection matrix? Also, thanks for all the matrix explanations. So not really. I mean, yes and no. Basically, this is the equivalent of a GL ortho call. So sort of we did, but we didn't re-implement GL ortho because GL ortho is slightly different. So you can take a look at GL ortho. I just wanted to show you how to do it because GL ortho is just a utility function. It doesn't do anything, right? Let me look and see if I can find something that has a better laid out version of that. Oh, nice. Good. That's good. Does somebody have the actual one that's not all typeset all messed up? This one's all messed up. The typesetting's all messed up. Yeah. Well, I mean, the typesetting is all messed up on that, so I couldn't quite point you to it, but essentially what's happening here is we're just doing our own version of GLOrtho that doesn't actually need to bother with the z coordinate, right? Normally GLOrtho actually still does depth, like it still has to do it still has to support z buffering. And z buffering is, of course, the thing where you actually track a depth value per pixel. It should properly call it depth buffering is probably the more correct term. But in order to support that feature, which we don't need and aren't using, they need to have the ability to actually generate proper z coordinates and do proper homogeneous coordinates there for the z. So their matrix is not going to be the same as this. It's going to be basically the same as this, but it's going to be a little bit different, right? And so if you look up GLOrtho and find a place that actually has it typeset properly, you will see a matrix that looks very much like our matrix, but it's not quite the same. The reason for that is it's not passing through these values the way that we are. It's actually putting things into the values that will get used for doing depth buffering. Let's see. I'm trying to see if there's any other Q questions. I don't see any. I see no further questions. So I think that's it. And hey, look, the stream has ended. All right, well, I guess that's all there is to it. Go ahead and save this so we can wind down. All right, thank you everyone for joining me for another episode of Handmade Hero. It's been a pleasure coding with you as always. If you would like to follow along with code at home, you can always pre-order the game on handmadehero.org, and it comes with the source code, so you can play around with it at home. But that is not the only reason to go to handmadehero.org. There's also a forum site you can go to where you can ask questions. There's a Patreon page you can go to support the video series, and there's a tweet bot that you can subscribe to know when the video series is going to be live, if that's your thing. That's about it, really. Yeah. Double check that tweet bot for the time for tomorrow, but I can tell you ahead of time, it's 5 p.m. Pacific Standard Time, right back here on Twitch. So if you want to follow with getting the OpenGL renderer running, which I think there really isn't that much more to do, we will cover that tomorrow and probably the next day. Just probably about 2 days would be what would be required. So yeah, hope to see you back here for that. Until then, have fun programming, and I'll see you guys on the internet. Take it easy, everyone.